Hello, PLDI. My name is Liam, and I'm going to be talking about some work on Quickstrom, which is a property-based testing tool for acceptance testing with LTL specifications. And this is joint work with Oskar Wikström from Sweden. So, what is property-based testing? Well, it's best exemplified by the Haskell library Quickcheck, which many of you may be familiar with. But there are property-based testing libraries for many programming languages these days. And essentially, it frees us from the obligation of having to specify the inputs to a function that we wish to test. Instead, we just specify the properties that we wish this function to satisfy. So for example, I say reverse of reverse x's without saying what x's is, just any list x's should be the same as the list x's. So if I reverse a list twice, I should get back the same list. And so here I haven't specified anything about what the list is that I'm going to reverse. And in fact, Quickcheck will just randomly select a large selection of different lists to test this property on. So in the bad old days, in the dark ages, fully being aware that the dark ages refers to a paucity of sources and not to an intellectual decline, we would have had to specify all of these inputs ourselves. So we would have had to say reverse of 1, 2, 3 is 3, 2, 1, and then the reverse of the empty list is the empty list, and many other cases like this. It's all very inconvenient. And this inconvenience means that people won't write tests. And of course, that's bad. We want people to be writing tests. We want people to be ensuring the reliability of their software. So what's acceptance testing then? So acceptance testing in traditional contexts would mean presenting the finished or candidate to be finished application in front of a user and getting the user to interact with it, and the user will determine whether or not this meets their requirements. Of course, sometimes users aren't available, or we'd rather automate this process in some sense. And so there are tools such as Selenium WebDriver for web applications where we can write a script that simulates the role of a user. And what Selenium WebDriver will do is simulate a browser and run the application in the browser, interact with it automatically, and then run tests as a result. So there are some properties that we can specify using Selenium WebDriver scripts fairly easily. For example, when I click cancel, I should return to the main menu. That's specifying the user's behavior as well as the expected result. So that's fine. We can do that in a very simple Selenium WebDriver script. Similarly, if I press the A key on a numeric input field, so pressing a letter on a numeric input field isn't going to produce any result, no text should appear, right? We can script that kind of thing in Selenium WebDriver as well. But we can't really script things that don't say anything about the behavior of the user and only specify the behavior of the application. So for example, if I say something like, I should not reach the secret page without logging in first, that doesn't say what I'm actually doing with the application. It just says this invariant must be maintained. Similarly, the menu should never be disabled forever, or after logging in, my username should always be visible. All of these sorts of properties might be reasonable to state, but we can't script them in Selenium WebDriver. So we're stuck in this dark ages of pre-property-based testing when it comes to this acceptance testing domain. So Quickstrom has the aim of solving this problem by bringing the magic of property-based testing to WebDriver tests. So how do we do this? Well, the user has to write a specification in our language, which we call Spectrum. And Spectrum is a pretty simple language. It's designed to be familiar to JavaScript programmers. And there's lots of details on the language in the paper, but I'm not going to talk very much about the language today. So I'll just give you a whirlwind tour of the language instead. So here's a section of one of the examples from our paper where we're specifying a timer application. So a very simple egg timer. So the first 3 lines here are describing state queries. So this is how we actually check information about the interface of our application. We're acting as the user here. So the only thing we can see is the externally visible state of the user interface. So what we have is the document object model in the case of a web application. So I'm saying that the label with the ID of toggle text is start in the first definition here, and that defines the Boolean value stopped, right? So this will be true if the label's toggles text is start. And similarly for started, if the label is stop. And similarly for time would be the amount of time that we have remaining in our timer application, right? So this is just describing how we can access the state of the application. The next thing we have are how we can interact with the application. So the first two actions are telling Quickstrom, for example, that we could click the toggle button if we wish to when we're in the stopped state, and that would be called the action start. Or we can click the toggle button when we're in the started state, and that's considered the action stop, right? So these are considered two separate actions, but because we've associated different preconditions to them. And then we've also got an action which is a changed action, and it's got a question mark instead of an exclamation point because this is a special type of action called an event. And this is an action that doesn't happen because of Quickstrom interacting with the application, but rather something asynchronous happening in the application. So for example, with an egg timer, it's when the timer ticks and something has changed in the application, we detect that change and we register it as an action that has taken place. So these are, we first need to define the state queries and then the actions, and then we can define LTL formulae that specify the expected behavior of our application. So linear temporal logic is a very common logic for specifying reactive applications, such as user interfaces. But I'll give you a brief introduction to linear temporal logic. So LTL builds on very basic propositional logic. So we've got a single state here, models of formula phi, where the formula phi could just be, atomic propositions and or not, all very basic propositional logic. What linear temporal logic does is extend this. So instead of referring to a model of just one state, sigma, it's referring to an infinite sequence of states. And we have a bunch of extra modal operators called temporal operators, which describe which of these states the formula phi is referring to. So if we have an unadorned formula, just an atomic proposition by itself, that's referring to the very first state, sigma 0. So for example, if I say this menu should be enabled, that's saying it will be enabled in the first state, sigma 0. I can say always or henceforth A, and that's the box modality, and that says that A will be true for all states starting from right now up and into the future. Diamond A, pronounced eventually or finally A, says that A will be true at some point in the future, so some sigma k. And next A means that A is true if we just remove the first state and consider the trace starting from the next state onwards. And A until B, that's what the U is saying that B will happen eventually, and at every state before then, A will be true. And release, which is the dual of until, which I didn't put in the semantics box there, just says that B has to be true unless A becomes true. So A frees us from the obligation of having B be true. That's another way to think about release. So with linear temporal logic, we can actually specify those properties that we couldn't specify before. I should not reach the secret page without logging in first. We can say either login releases us from the obligation of not being in the secret page, which is one way of looking at it, or we could also say it is not the case that I will reach the secret page, and before then I will not have logged in at every state before then. Alternative, for the menu should never be disabled forever, I could say it is not the case that at some point in the future, from that point onwards, the menu would be disabled. And the other property that we wanted to specify was after logging in, my username should always be visible. We can just say at any point, if I've logged in, then forever afterwards, my username should be visible, right? So this is just to give you a bit of an intuition for linear temporal logic if you haven't seen it before. Okay, so we have Quickstrom, and we have our application, and it's interacting with our application. And it's going to make some observations of our application, this sequence of states. And this sequence of states is a trace. And what we want to do is check our formula phi, well here phi 0, against this trace. Now there's many ways to do this. we chose to do the very simplest way to do this, which is to exploit these expansion identities that are part of any LTL variant. Essentially, we can say, if we have a next operator, we can say always phi is the same thing as phi is true right now, and in the next state, always phi is true again. And similarly, eventually phi says that phi is true right now, or in the next state, eventually phi is true. And until and release and all of the other temporal operators can be expressed this way, which means that we can sort of create an operational semantics for linear temporal logic, where we just progress a formula state by state to get the formula that should be true for the remaining trace. So this means that we can just move our formula along, evaluating it by formula progression each state along in the trace, and simplifying it at each step to prevent the formula from blowing up too much in size. At least for all the practical cases we've tried, this does simplify it sufficiently. So now we can see if we have a formula that is satisfied by a finite prefix of our trace. For example, in 3 states I should have exited the application is a property that would be easily satisfied by a 3-state trace, then we can get that conclusive answer, true or false, just by doing this. But most of the time when we have an LTL formula, it's going to use one of the temporal modalities like always or eventually, which means that we're going to hit the end of the trace at some point, and we need to decide what to do about that. The problem is we've hit the end of the trace here. We're at phi 6, state 6, and there's no more states to get, right, in our trace. So what does next x mean if there's no more states? It's a bit of a problem. Noeli has a finite variant of LTL where he splits the next operator into 2, one which defaults to true and the other which defaults to false. So we can give a sort of presumptive answer this way. But the problem is this finite LTL is for completed traces, but these traces are partial in the sense that the application hasn't finished running. It's just our testing tool has decided to stop at this point. So we take a leaf from runtime verification applications of LTL, and there's a runtime verification variant of LTL which distinguishes between definite answers that we can make based on the partial trace that we've seen so far, and answers that we have to just, well, if this is the last state in the overall trace, then we'd give this answer. But if you extended the trace a bit further, you might get a different answer. So we can distinguish between these two cases. But there's still a problem here. For example, if I have always eventually menu enabled, this property we saw before, then if we happen to end up if we have an application which is alternating in these states, menu enabled, menu not enabled, menu enabled, menu not enabled over and over again, and we just decide to stop testing at the point where the menu is not enabled, then this property would be false, even though it clearly is true if this alternation were to continue. So how do we solve this problem? Well, we just don't have to settle for partial traces all the time. We can ask Quickstrom to do more actions and get more states and extend our trace as far as we like. It has to be finite, but it doesn't have to be this length. It can be any length we need. So what we do in Quick LTL is add a new next operator, which, if invoked at the end of the trace, requests Quickstrom perform another action to generate a next state. So then we'll get another state, and then we can progress our formula further. And we can keep doing this until we have no more demanding next operators. So our temporal operators are therefore annotated with natural numbers, so for example, always 100 not crash will require at least 100 states to be convinced it's true. And this is defined inductively using the weak next at 0 and the demanding next at any other n. And similarly for eventually. So this subscript basically determines how deeply Quickstrom will look before giving up, right? Either assuming it's true or assuming it's false, depending on whether it's a safety property like always not crash, or a liveness property like eventually initialized. So there's this trade-off here between testing time, because the more actions we take and the more states we produce, the longer it'll take, and testing accuracy. So we applied our framework to the ToDo MVC benchmark, which is a benchmark that works for is for basically every web application framework has implemented this ToDo app, and we formally specified it, and we tested every single one of the implementations, and we ended up with a very alarmingly high failure rate for a lot of these applications. So there's a lot of bugs here, and all of these are pretty legitimate bugs. You can see the paper for details on the bugs. And we also found that if we look at the subscripts that determine how far Quickstrom should look in the trace and how many actions it should do to produce a trace, the longer the trace is, obviously the longer it takes in a linear relationship, but we find the vast majority of bugs with only a trace length of 100. Any further increase in this trace length gives you diminishing returns. All right, so there's a lot more details in the paper and information on the bugs we found, Quickstrom's architecture, the Spectrum language, and so on. And this is an open source project, so we welcome any contributions. I'm also looking for a PhD student possibly in this area, so if you're interested in that, please get in touch. Thank you.
All right, thank you so much for the talk. Once again, a talk where one of the questions I had was answered in it's all the always eventually case is a really tricky one to think about with finite traces, and then it's the example you have. So we have time for questions now. Again, you can post on Slack or in the Gather town. I guess one question is about the writing of the properties themselves, right? So I understand that the authors wrote some of the properties for the evaluation of this paper. Have you interacted with? I know LTL is sometimes a tricky thing for people to get their minds around. So have you interacted with anyone about Spectrum and how that language could be used by non-experts?
So that's a great question. Perhaps my co-author Oscar would have been better suited to answer it, because he's actually applying Quickstrom in industrial contexts and teaching JavaScript programmers how to use it. But at least from my impression of how things are going, perhaps the notation of LTL is a little bit hard to get your head around. And the other thing that is difficult is it's sort of unclear, because if you say, for example, the box operator means always, then if the box operator is nested, it's eventually always, it's not clear to people that always applies from the point where the eventually operator leads you. And so it's sort of unclear that if you give an informal semantics of LTL, which is commonly how people try to get introduced to it, they don't quite make the connection that these temporal operators actually can be nested in that way, and nesting temporal operators is the really confusing part. We're still working on ways to educate developers about this, but we do think that LTL is the best way to specify these kinds of properties that people want to say in a formal way.
Right. Yeah. Does Spectrum actually have the square and the diamond
it doesn't
in it?
It doesn't use that notation. Okay. It uses words like always and so on. Yeah.
Okay. So I would hope that words are simplified.
I'd hope so. Yeah.
Right. And I guess just one other question. I know you had a bunch of bugs. Have you heard anything about? Have you submitted any of those bugs or heard anything about the maintainers of them?
So this is another good question, and something we did try to do. So we did investigate the causes of all of the bugs, and we've identified a lot of them. But the problem is we can't really fix the bugs ourselves. We don't really know these web frameworks. We did submit pull requests, or rather just a bug report to the ToDo MVC maintainers, but they are quite unresponsive, it seems. So it might be worth for us to actually contact the developers of each individual implementation with the bugs that we found, rather than the maintainers of the overall project, because they don't seem to be responding to us.
They might not know the individual implementation.
Yeah.
All right. Well, thank you so much. I think that's the time we had. Thanks.